Now we're going to work on a really cool application of the algorithm you just solved. You can proceed with the project guide PDF and start sketching how the 3D mapping is going to work using stereo cameras on a moving vehicle. For street-side mapping, we are looking to project a 3D model of a street with 5 houses using a car with 2 cameras. This mimics the real-life recording and mapping of streets and houses, like how Google Street View cars provide the visuals you see in Google Maps. Let's talk about how these cameras are going to work. Let's say the camera is here, and point P is here. The camera is going to be able to give us a direction called ray outgoing, which points to point P. Unfortunately, this camera doesn't give us a distance. We have a direction, but not a distance, so we're unable to output a coordinate with what we have here. It's unsolvable. But what if we had 2 cameras? Let's copy that and say we put a second camera right here. The second camera is going to give us another ray, but it's going to point in a different direction than the first one, since it's looking from a different position. Now it's solvable, because we have 2 lines from the cameras that we can find the intersection point of. Alright, now let's look at our givens for this problem. We've got our poses for both cameras. This gives us the position and orientation of the camera. We're also given the outgoing rays for both cameras. These outgoing rays are in the camera's local coordinates. So let's set up our coordinate spaces for both the world coordinates and the camera's local coordinates. The transformation going between them are going to be coordinate rotate and coordinate unrotate with the pose as the input. Also, we're only going to be focusing on one camera, as you can see, since the pseudocodes will be the same for both until we intersect them. Let's visualize everything. We'll say this is the camera pose in world coordinates, and that the outgoing ray is going this way. So the outgoing ray in local coordinates will look like this. Our result will be the infrared point. Now we need a way to get 2 lines to intersect at the infrared point. As I explained earlier, we're going to try to intersect the rays, so we'll first have to find the rays in world coordinates. Right now they're in local coordinates. In other words, we have to find the outgoing ray using ray prime. As we can see by the transformation between the 2 coordinate spaces we visualized, we'll simply have to unrotate ray prime by the pose's orientation. Let's write this down. In Dataflow geometry, we can't intersect rays. We haven't made an algorithm for that. But we do have an algorithm to intersect lines, so let's represent these rays with extended lines. This will be really simple, because we'll just use the ray as the direction. We also need a position, a point on the line, which will just be the position of the camera. You can extract the position of the camera from the pose. Alright, now we've got the line representing the ray in world coordinates for our first camera. I mentioned earlier that the second will literally be the exact same thing, using the givens for camera 2. Let's copy that quickly. Because of rounding, we won't get a result if we actually intersect these lines. They'll be so close, but not exact enough to give us a single point. We can easily bypass this though. We can just use bridge skew lines to find the super short line segment where our lines are supposed to intersect. We'll just find the midpoint of that to be more accurate for our final result. When you open up the 3D Cartesian workspace, you'll see the car with a red and yellow camera. When you click Start Mapping, it's going to be projecting all the points of the 5 houses and should play out like this. Isn't it interesting how this complex Google application can be broken down into just a few advanced algorithms? The next place we're headed is working with spheres and their intersection.